For many years, stories of strange flying objects in the sky were often dismissed as imagination, illusions, or misidentified aircraft. But now something has changed. Even official defense and space organizations are beginning to acknowledge that unidentified aerial phenomena, UAPs, once called UFOs, are real, captured by advanced sensors, and often behave in ways that defy conventional science. This shift has brought the topic from the fringes into serious scientific discussion. So, what exactly are UAPs? UAPs are objects observed in the sky or sometimes underwater that remain unexplained after careful analysis. These are not just based on eyewitness stories. Many are recorded by high-resolution cameras, radar systems, infrared sensors, and satellite tracking. Often, these phenomena are observed by experienced pilots and technical crews, sometimes by multiple systems at once, making them difficult to ignore. You might ask, what makes these objects so unusual? Reports often describe smooth, silent, wingless craft shaped like spheres, disks, or tic-tacs that hover, dart, or accelerate with extreme speed. In some cases, these objects change direction instantly, stop midair without drifting, or descend into the ocean without making a splash. These are not characteristics of any known aircraft, bird, or drone. Some UAPs appear to outmaneuver modern tracking systems, behaving as if they are guided by technology or principles of motion that are not yet understood by physics. Is this just speculation? Actually, no. Numerous sightings have been confirmed through instrument-based data, not just visual observation. In several well-documented cases, objects were recorded on multiple sensors at the same time, visual, radar, and thermal, making it hard to dismiss them as illusions or glitches. Experts who reviewed these cases confirmed that the object's movements and energy signatures do not match anything familiar in aeronautical engineering. Could they be advanced technology? That's one possibility, but scientists and analysts point out that even our most advanced systems struggle to explain the energy source, stability, and sudden acceleration shown in some of these cases. These behaviors would require materials and propulsion far beyond our current limits. Others have suggested that the phenomena could be a result of plasma effects, atmospheric anomalies, or unknown natural forces, though these theories are still speculative. Why are scientists now getting involved? Because UAPs represent an open question, a true scientific mystery. If something is flying, hovering, and accelerating in ways we can't explain, that's not science fiction. That's a call for deeper investigation. Leading researchers are now building dedicated observatories and sensor systems to capture high-quality data on these events. They are using AI and machine learning to analyze thousands of hours of sky footage, looking for patterns that might reveal what these objects are and how they work. What does this mean for science? It opens a door. UAPs challenge what we think we know about aerodynamics, inertia, propulsion, and even perception. If something is moving through the air with no wings, no visible engines, and no heat signature, how is it doing that? Could there be unknown energy forms or new physical laws that we haven't yet discovered? These are serious questions, and researchers are now treating them with the same rigor as any scientific mystery. So the next time you hear about UAPs, ask yourself, if trained observers, high-tech instruments, and physical evidence all suggest something unusual is happening in the sky, is it really just fantasy? Or is it a rare opportunity for science to confront the unknown with an open mind and the right tools? Modern UAP investigations rely on data fusion from radar, infrared cameras, and high-speed optical filming to validate sightings. Radar provides precise measurements of range and velocity, while infrared detects heat signatures indicative of propulsion. Optical footage captures shape, reflectivity, and movement details under varying light conditions. Advanced algorithms correlate these streams to reconstruct three-dimensional flight paths. Cross-validation among sensors reduces false positives and refines object characterization. A fast-moving object was simultaneously recorded on radar, thermal imaging, and video, confirming abrupt altitude changes. It is like using a GPS tracker, speedometer, and dash cam together to verify a vehicle's route and speed. UAPs often generate radar echoes that vanish or shift unpredictably, defying typical aircraft signatures. Sudden signal dropouts suggest either rapid cloaking or sensor saturation. In other cases, reflected waveforms show unusual scattering patterns, hinting at unconventional surface properties. Analysts study variations in signal-to-noise ratio and Doppler shifts to distinguish real objects from atmospheric artifacts. Understanding these anomalies improves detection reliability and sensor design. During an exercise, a radar return disappeared instantly when the scanning frequency changed. It's like a mirror turning transparent when you shine a flashlight at a specific angle. Eyewitness and instrument reports describe UAPs making instantaneous accelerations, sharp turns, and rapid halts without visible control surfaces. Such maneuvers imply acceleration forces far beyond the tolerance of known materials and occupants. The lack of sonic booms during high-speed events suggests novel means of shockwave mitigation or non-aerodynamic thrust. Researchers model speed vs time profiles to estimate the thrust-to-mass requirements. These dynamics challenge current aerospace engineering limits. An object was tracked abruptly shifting from hover to high-speed forward motion without an audible sonic crack. It's like watching a skateboarder teleport from one spot to another without rolling. Some UAPs display glowing halos, color shifts, and refractive distortions that resemble ionized gas plumes. High-energy interactions can strip electrons from air molecules, creating localized plasma and visible corona discharges. Observers note brightness variations as altitude and atmospheric pressure change. Spectral analysis of these glows can reveal emission lines of excited atmospheric gases. Differentiating engineered light emission from natural plasma phenomena is a key research focus. Video footage showed an amber ring surrounding an object, later identified as excited nitrogen emission. It is like the colorful halo seen around a high-voltage power line in foggy weather. Encounters with UAPs sometimes coincide with temporary loss of radio communications, GPS glitches, and sensor malfunctions. Such disruptions point to strong electromagnetic fields or deliberate jamming techniques. Engineers measure frequency drift, bit X rates, and magnetic field anomalies to quantify interference. Mapping these effects around sighting locations helps define the spatial reach of the phenomenon. Understanding the underlying electromagnetic mechanisms informs both detection and countermeasure development. During a close pass, onboard systems went dark for several seconds before recovering when the object moved away. It's like your smartphone losing signal when you stand too close to a powerful magnet. Recent releases of de-identified sighting logs, sensor recordings, and witness reports have enabled independent researchers to conduct statistical studies. Standardized data formats facilitate cross-case comparisons of speed, altitude, and maneuver profiles. Open databases allow pattern detection algorithms to identify recurring flight corridors and behavior clusters. Peer-reviewed analyses help separate anomalous cases from misidentified natural events. This collaborative approach elevates UAP study to a data-driven scientific discipline. A publicly available database revealed a cluster of rapid descent events near coastal regions during certain seasons. It's like pooling crime reports into a shared map to spot hotspots and trends. Individuals near UAPs sometimes report headaches, nausea, or fleeting memory lapses, suggesting exposure to intense fields or stress. Controlled experiments monitor heart rate variability, brain waves, and hormone levels before and after simulated sightings. Double-blind studies with sham events help distinguish real physiological effects from psychological expectancy. Long-term health monitoring evaluates any lingering impacts of repeated exposures. Ethical protocols ensure volunteer safety and informed consent throughout these investigations. Test subjects exposed to strong low-frequency fields reported transient dizziness similar to motion sickness. It's like feeling woozy after standing too close to a high-powered radio antenna. To explain UAP performance, researchers examined theories ranging from electromagnetic drive concepts to spacetime curvature manipulation. Laboratory tests of high-intensity electromagnetic cavities aim to detect minute thrust without propellant. Theoretical frameworks extend general relativity to consider localized metric alterations. While conclusive demonstrations remain elusive, these investigations broaden the known boundaries of propulsion science. Rigorous peer validation ensures only reproducible results advance the field. Experimental thrust on the order of micronewtons was reported in an electromagnetic drive prototype under vacuum conditions. It's like hypothesizing a car engine that uses the fabric of the road itself to push the vehicle forward. Unexplained aerial objects present potential hazards to other aircraft and infrastructure if left unaddressed. Airspace authorities update monitoring protocols and pilot advisories to include erratic trajectories. Collision avoidance systems are tested against simulated UAP profiles to ensure reliability. Real-time data sharing networks enable rapid alerts to relevant stakeholders. Understanding and planning for UAP encounters is essential for maintaining safe skies and critical operations. Real-time alert systems notified nearby aircraft of an erratic object entering their flight path, allowing safe, evasive maneuvers. It's like adding an extra sensor on a car dashboard that warns you of unpredictable obstacles ahead.